Hi, this is Ashley Bedford with the Runtime Diaries, and we are so excited. Today is day 7 of the hashtag 30 Days of Code with Educative Challenge. Today's problem, we are going to convert a sorted array into a BST. It's easy, so let's dive into the walkthrough. Today we're tackling the convert sorted array to BST LeetCode 108 problem. This one is all about transformation. How a simple sorted array can become a perfectly balanced binary tree. We'll go from a naive recursive version to the efficient index version and finally to a fully iterative stack-based build. So what's the setup? We're given a sorted array of unique integers, like from left to right, 1, 2, 3, 4, 5. Our goal is to build a height-balanced binary search tree, which means the depth of the left and right subtrees should never differ by more than 1. And finally, we return the root node of that balanced tree. Balanced is key here because it keeps all future operations like search and insert efficient. Let's think about why BST is a perfect match. A BST's in-order traversal always gives a sorted list of values. So if we start with a sorted list, we can reverse that idea. Use the middle element as the root. Everything left of that number becomes the left subtree. Everything right becomes the right subtree. That one insight ensures that the tree grows evenly and stays height balanced. It's symmetry in action. Left is less than root, which is less than right. Now, let's start with the simplest possible code. In the naive version, we recurse directly on list slices. We find the middle index, create a new tree node, then build the left and right subtrees by slicing the list, as you can see by the 2 lines in the highlighted code block below. It works beautifully for small inputs, but here's the catch. Every slice creates a new copy of part of the list. So each level of recursion is duplicating memory over and over again. It's correct, but it's inefficient. Because of all those slices, our time complexity balloons to O of n log n. Each recursion level copies roughly n items in total, and we do that log n levels deep. The space complexity also hits O of n log n, since every slice is a fresh list. So, even though the logic is clean, it's quietly wasting resources. Our fix is to stop duplicating lists and reuse indices instead. Here's where things get smarter. Instead of slicing lists, we'll keep one array and simply track where each subarray begins and ends using indices. This small structural change eliminates all the copying. Our new key line is mid equals left plus right minus left, floor division by 2. It computes the middle index safely within the current range. This is the foundation of our first big optimization. Now here's what the code looks like. We define a helper function that takes left and right bounds instead of a new list. Each call picks the midpoint, creates a node, then recurses left and right. So take a look at the helper functions using the left and mid minus 1 indices and also the mid plus 1 and right indice. No slicing and no copying is occurring here, just pure index math. Each element is touched exactly once, so the time complexity drops to O of n. And the call stack depth, since the tree is balanced, is O of log n. Let's summarize that improvement. Time O of n means every element becomes one node and we never duplicate data. The auxiliary space O of log n, well, that's just the recursive call stack. This single change removes all unnecessary overhead while keeping the algorithm easy to read. You just eliminated an entire login factor. That's the real optimization here. There's one small nuance we should address: even length arrays. If you have an even number of elements, there are two possible middles. You can choose either the lower middle or the upper middle. Choosing the upper middle tends to produce a slightly better balance, so we can compute it safely with mid equals left plus right minus left plus 1, floor division 2. That extra plus 1 tilts toward the upper index. It's subtle, but worth understanding. So far, we've improved efficiency, but there's one more layer: structure. Our recursive code is elegant, but Python's call stack can only handle about 1,000 recursive calls before throwing a recursion error. What if our input list has 10,000 elements? That's where structural optimization comes in. We replace recursion with our own explicit stack, turning the same logic into a while loop we control. Same idea here, but now we manage the call stack. Here's the final optimized version. We start with a single stack item representing the full range O to n minus 1 and no parent. Then we loop. Pop a range, pick a midpoint, create a node, attach it to its parent, and push the right and left child ranges back onto the stack. The result is the same balanced BST, but without recursion. It's safer for large inputs, easier to debug, and performs just as fast. Let's talk about results. Time complexity? It's still O of n. Each element becomes one node. The space complexity? It's still O of log n on average, because even though we now use a manual stack, its depth mirrors the same tree height. So why bother restructuring? Because now we have more control, no recursion limits, and the exact same efficiency. It's structural optimization. It's not faster in theory, but it's more reliable in practice. Let's visualize it with a real example. Our input array from left to right is -10, -3, 0, 5, and 9. Pick the middle 0. That's our root. Our left side's going to be from left to right, -10 and -3, which builds its own subtree. The right side from left to right, 5 and 9, builds another. The result is a perfectly balanced BST where left holds smaller numbers, right holds larger numbers, and the depth difference is less than or equal to 1. Simple, predictable, and efficient. Before we close, let's reflect on what we learned. Here's some common mistakes. Returning 0 instead of none for any empty children. Using list slices in recursion. Forgetting about even length middle choices. Not handling empty inputs gracefully. And here's some key insights. Think in ranges, not slices. Understand the difference between Python's hidden call stack and your own explicit one. Structural optimization doesn't always change complexity, but it does change control. And that's a wrap of day 7 of our hashtag 30 Days of Code challenge with Educative. If you're learning DSA with me, join the challenge by clicking on the link below to get 10% off of your Educative plan. Super excited to continue to grow and build with you all. We are still going to keep up with our walkthroughs, so that is another plus of joining. We will see you all for day 8 tomorrow.